speed versus velocity. Now the first thing we're going to talk about is speed. Speed. There. So we're talking about speed. And our symbol for speed is a lowercase v. Our unit for speed is the meter per second, which we write as m per s. And strictly speaking, it's the distance traveled per time. Distance traveled per time. So velocity is going to be that distance divided by time, or x over t.
Wait, v is the symbol for speed?
V, and it'll make more sense in a minute. Why we use v. Okay? Which is why we call it speed versus velocity.
Is this
Notes. Lecture notes. These are lecture notes. You should be continuing this after the frame of reference stuff we took last time. Just continue. So this is chapter 2, 3 notes. So our symbol, V, meter per second. And we need a little more time.
Yeah. Oh.
Now, rates. So I'll mention rates here. Now, rates are anything per time. If you do anything per time, it is a rate. Speed is a rate. Is a rate. But there are lots of rates. Anything done per time. Like our speed is distance per time, which we have meters per second. We're going to learn about acceleration here in a second. And acceleration is the change in speed per time. We measure that in meters per second squared, or which also means meters per second per second. We also see things like pumps. If you look at the ratings of a pump, they say pump ratings, gallons per minute. You see it GPM, something like that, gallons per minute. Anything per time is a rate. Like current, stuff travels through the wire. How many coulombs of charge per second? That's a rate. Anything per time. Okay, so remember that, anything per time. Anyone need more time? So, which leads us to velocity. It's mentioned. Velocity. Why is speed a v? Well, because velocity. We get it from velocity. Our symbol is a v, and you think, well, that's the same as speed. Well, that's because speed is part of velocity. Speed is the how much part of velocity. So velocity is speed in a direction. Speed in a direction on that. Our unit is still the meter per second. Now in lab, generally we deal with speed part of it. We're measuring things because we're only going in one direction. But remember, velocity. If I said I'm going on I-280 at 65 miles per hour, does that give you the whole story? So that would be my speed, but am I going towards San Francisco or am I going towards San Jose? That's velocity. So I'd say I'm going 65 miles per hour north, I'm going 65 miles per hour south. That's a velocity. So speed is the how much, but direction, it makes it a velocity, speed and direction. So we also need something called displacement. Now we have distance. Distance is how far you travel. Just the length of distance your thing travels. In your car, you have a little device that tells you distance, and that's called a what? Odometer. Odometer tells you distance. But displacement is the distance and direction from a starting point. Now, in both of these are what we call vectors. A vector. That's one of your vocab words. A vector. Remember, a vector has a how much part, a magnitude, and direction. We have a how much part and a direction on that. So, and this is where positive and negatives come in. We start dealing with vectors. You've got to get out of your heads that a negative number means subtraction. Okay? Positives and negatives are directions. They are opposite directions. Because if I'm going up, how do I specify I'm going down? Well, if I say up is positive, then down direction would have to be negative. If I say north is positive, south would have to be negative. And does it matter which is which? No. However, by convention means this is kind of how everybody does it. We usually say up is positive, down is negative. Right is positive, left is negative. Why? Well, look at a Cartesian coordinate system, right? If you go up on the coordinate system is positive, go down is negative. Go to the right is positive, left is negative. So also, if you were overlaid on the map, north is positive, south is negative, east is positive, west is negative. You know, but think Cartesian coordinates, that Cartesian coordinate system on that. All right, displacement, how does it work? So this is my starting place. I'm starting right here. I start right here. And I go 1, 2, 3. I take 3 steps. Now, how much distance have I traveled? 3 steps. My displacement is 3 steps toward the windows. I take 2 more steps. 1, 2. Now I have traveled 5 steps total, and my displacement is 5 steps toward the window. I turn around, and I go back 1, 2, 3, 4. How much distance have I traveled now? I traveled 9 steps. That's the distance I traveled, right? I went 5 out and 4 back. Distance. But my displacement is 1 step toward the window. You see the difference here between distance? This is how far I actually traveled. Displacement is how far I am from my starting point. And if I take 2 more steps, well, now I'm 1 step toward the wall. So I've gone through my starting point, but I've traveled a total of 11 steps. And if I take 1 step back this way, my displacement now is 0. So I'm back on my starting point. But I've traveled a total of 12 steps. So it's just between distance and displacement. Distance is how far I actually travel. Displacement is how far I am from my starting point. Okay, on that. Hopefully every day you guys end up with by the end of the day, you end up with a displacement of 0 because it means you've gone back home. All right, so on that. A little bit on that. So how do these work? Now, a couple of things we need to understand. Average and instantaneous velocity. Average velocity. And usually we're talking the speed part. Now, these formulas we talk about are the magnitude part. Okay, just remember that. They are the magnitude part of that thing. So the total distance traveled divided by the total time. It does not tell you, tell speed, velocity at any particular time. So it doesn't tell what you're doing at any particular moment. This is what the average over your whole trip was. You know, let's say we went to LA. We're going down to LA, and we drove 400, about 400 miles. So we went 400 miles, and it took us 8 hours to get there. For whatever reason, it took us 8 hours to get there. Which means, since my average, V average, that's what we do here, is that total distance traveled divided by the total time. Another way to write it, we usually write it like this: delta x over delta t. That Greek letter delta means difference in on that. That's what it means, difference. Which basically means my start minus my finish. Since our start is 0, my finish distance minus my start distance. Distance time, end time minus start time. End, start minus start. So that's what that means. Now, if I was doing my trip here, my average speed, so velocity equals 400 miles, that's divided by 8 hours, I would find, well, my average speed was 50 miles per hour. Now, if you've ever been on Interstate 5, Is the speed limit 50 miles per hour? No. More like 75 miles per hour. 70, 75, depending on where you are. So why is my average 50? It could be traffic. I mean, if you've ever driven to LA, once you get to LA, I mean, you're lucky if you do 50 miles per hour. Well, we're talking most cars, we're talking just driving the speed limit. But also within that 8 hours, did you probably have to go get gas? Probably at some point you had to stop for gas. Probably somebody started for a meal, stopped to go to the bathroom, stopped to see the largest prairie dog in the world, stopped at Starbucks, things like that. So remember, so within this 8 hours, were you always driving? No. And there's also traffic, as mentioned. There's different places. This is why when you get those little things off like MapQuest and the things, the map things, the Google Maps, this gives you directions, say it should take you such and such amount of time. And you probably looked at it, we got in there, well, it took me less time than what it said. Sometimes it takes me more. But they have an average speed built in. They say, well, on average, you should be able to take an average speed of this. It calculates how much is city streets, how much is this, and they base that time based on that average speed on that, how long it should take you on that. Obviously, it doesn't take into account traffic jams and that sort of thing. So this is average. Average velocity doesn't tell you what you're doing, just tells you over the whole thing. It's all the distance divided by that. By the way, there's another way to find the average. Also, you would take your average velocity could also be, and this is what we're going to kind of do in your lab, is the beginning, is your ending velocity minus your beginning velocity divided by 2. Just it's like a regular average, or add it up. So the beginning minus the end plus 2 divided by 2 would also give you an average velocity, which we're going to see. We kind of use both of them together on that. Now, instantaneous velocity is your velocity right now. What device in your car gives you your velocity right now? Speedometer tells you right now, right this second. And it's the velocity at any particular instant. That would be your speedometer. We also get it from the slope of a distance time graph. Distance time graph, the slope of that line will tell you your instantaneous velocity at that point, which is one of the things you're going to be doing next time. That's why we're doing this exercise today, is to get data so we can graph and do some of this velocity next time. See these graphs. Another one that gives you that is police radar. Police radar gives you instantaneous velocity. And you could be driving under the speed limit all day long. You've been driving all day long. You were under the speed limit all day long. But for 30 seconds, you went to pass somebody, you were over the speed limit. 30 seconds, you've been driving for 8 hours. 30 seconds, you over. Guess what? If the police get you in that 30 seconds, what's going to happen to you? You get a ticket. Say, well, this is the only time I've been over the speed limit. Because, see, what says on the radar? Write your ticket. So there, instantaneous. What you are this very second, not what your average is over time. Questions? One need more time. Now, a couple of terms we need to do, because they also include other things. Constant versus changing velocity. When we say this, especially when we say this word constant means non-changing. Speed and direction are always the same. Speed and direction, because we're talking about velocity. It also means our acceleration is going to be 0. Later on, we're going to learn it also means the net force is 0. But if we are going at a constant velocity, by the way, notice this, acceleration is 0. Does that mean we're not moving? No. It means we're not accelerating. You have to get it straight in here, especially a lot of people want to make them the same thing. Velocity, acceleration are two different things. They are related to each other, but they are giving you different information. Velocity is how much distance you travel in a period of time. How much distance. Acceleration is the change in that velocity. But changing velocity can be a speed changing. Could be your speed changing. Like you hit the accelerator, you speed up, you hit the brake, you slow down. Could be a direction changing. You're on the merry-go-round. Merry-go-round goes at a constant speed, but it's constantly changing directions. Things going around in circles are always changing their direction as far as circular motion. Or both can be changing. All right? That'd be our acceleration. Acceleration is not equal to 0. And there is a net force not equal to 0 on that. Any questions? Which is to lead us to talk about this changing velocity. We have a term for a changing velocity. So is anybody ready? Anybody need more time on this slide? And we call changing velocity acceleration. By the way, acceleration is most people think acceleration, speed increasing. Acceleration is also speed decreasing. The word decelerate is not a physics word. You're either accelerating in the same direction of motion or accelerating in the opposite direction of motion. So our symbol for this, our symbol is a lowercase a mostly. Our unit is the meter per second velocity per time, which we usually don't write it that way. You know, if we wrote it this way, it's kind of cumbersome. But if I have a fraction over a denominator, what happens to the denominator of the top fraction? No, that would be if it was on the top. It goes to the bottom. So this becomes meters per second times second, or meters per second squared. This is why the unit is meters per second squared, because it's really meters per second per second. I mean, if you are if you're a car person, you like to do road and track and those kind of things, they'll give the acceleration of the cars. They'll say like miles per hour per second. You know, how many miles per hour is your acceleration per second you increase? So that's an acceleration. A change in the speed per time. Remember, it's also a change direction. This is also a vector. This is a vector quantity. Because does it matter which way I push something? Does it matter which way I accelerate as to how if I'm going to slow down or speed up? And this can be that change in speed, direction, or both. And our acceleration is the change in velocity per change in time, which is that delta V over delta T. Remember that Greek letter delta, change in. Now, this is where that positive and negative thing can get confusing. All right? We are going to call toward the windows positive, toward the wall negative. Now, my motion is toward the wall. I have positive velocity. My sign would be positive meters per second. I apply an acceleration, a positive acceleration. Notice they are both in the same direction. Is my car going to speed up or slow down? We are going to speed up because we are accelerating in the same direction. Now, that'd be like hitting the gas pedal. Now, I am going this direction, but I apply a negative acceleration, which would be an acceleration in this direction. Now, the motion and the acceleration are in opposite directions. My car is going to, slow down, come to a stop or something. But notice, our acceleration is in the opposite direction. Now, I'm moving toward the wall. Now I'm moving that way. I have a negative velocity. I apply a negative acceleration. Remember, it's negative acceleration. It's just acceleration in that direction. Am I going to speed up or slow down? I'm going to speed up because those are both in the same direction. I'm going in the negative direction. I apply a positive acceleration. My car is now going to slow down and may come to a stop. But notice they're opposites. So this is where you have to be careful of that positive and negative. Just because you have negative acceleration doesn't mean it's not going to get bigger. If the motion and acceleration have the same sign, either both negative or both positive, it gets bigger. They're opposite, it's going to get smaller. This especially comes when we deal with things falling. Because generally, things fall gravity is negative because it's down. Because we define everything going down as being the negative direction. Up is positive, down is negative. So you have to be careful of that. Obviously, when you drop things, they get faster, right? Have you ever had a case where you dropped something and didn't go faster? Far in air resistance, but that's a whole other story. Now, and so we're done there. All right, so we are kind of done for the moment on that. So, graphs. Now, we do not do graphs in here for the sake of doing graphs. I am only going to have you do a graph in a lab because the answer to the problem is going to come from the graph. In fact, that should be your clue. If there's a graph in the procedure, it's like, oh, my answer. The answer to my hypothesis is going to come from that graph. All right? So, lines on graph give information on relationships and values. There's different kinds of lines. So lines can be straight, lines can be curved. The line, now you guys have lots of experience with straight lines and things like that, generally from algebra. The main thing about the algebra curriculum, and it's not a fault of the teachers here, because I taught algebra myself, has to do with the state standards. The one graph you don't do in algebra is the scatter graph, which is really the only graph that you do outside of algebra. Okay, so remember, our lines are not going to all plot on ice. It's like all the dots go down, the line goes on the dots. It doesn't do that. We do not connect the dots, which is one of the reasons we use that graphing program. Because to get these relationships, sometimes you have to check different relationships, and it gives you a better graph on that. Now, straight lines. Straight lines, one, are going to tell you something's constant, especially any graph that's a rate. Graphs that do rates. Remember, and rates are anything per what? Per time. Anything per time. And when we're dealing with rates, we have those rates. When we deal with rates, time is going to be on the x-axis. In fact, the two graphs you're going to make, the two things you're going to do graphs with next time are rates. Are rate graphs. Okay? So you're going to put time on the x-axis. Now, the other thing it shows is something directly proportional. That's what actually we are going to make some graphs for the lab we're going to do next week. You are going to make some graphs, and that's going to be a directly proportional relationship. You're looking for the straight line. In other words, if something goes up, the other thing goes up too. That's directly proportional. If this goes up, this goes up. If this one goes down, that one goes down. They go up and down together. That's directly proportional, and it will be a straight line on the graph. A straight line on the graph. On that. Anyone need a little more time? Now, curved lines. Curved lines represent other relationships. Could be an inverse relationship, an inverse square relationship. It could be different powers. So curved lines, different things. Ones we do a lot are the inverse and inverse square, which is also one of the reasons we use that computer program. Because you draw an inverse or an inverse square by hand, it's very hard to tell the difference. But the tools within the graphing program will allow you to make a determination which line does your data match up to. Because an inverse and an inverse square look very similar on that. Some lines have no mathematical relationship. In other words, we just get our experimental data and we plot it out. And you plot it out. It just is where they are. I'm going to show an example here of some intensity, an intensity of some sort of light versus its wavelength at a certain temperature. Say this might be a filament from some sort of light bulb. So you can see how bright is it in different colors depending on temperature, and that can vary, how things glow and things like that. I also example in the Navy, every ship has a set of curves, lines for how that ship reacts, say when you go from salt water to fresh water. In other words, with this loading condition, in this water, at this temperature, you should be at this draft. What should it be in salt water, fresh water? Because as you move from salt water to fresh water is denser than fresh water, so your ship actually goes farther down in the water. So like if you go from the ocean into, say, the bay, which is more fresh water, we're going to go farther in the ocean. You go up in the Sacramento River, which is salt water, or it's fresh water, your draft is going to be deeper on that. So you worry about that. And you might think, well, it's a big ship and a big channel, but sometimes these channels aren't always that much bigger than the ship. I know in Missouri, we actually made the channel in Pearl Harbor a little wider one time, because we kind of scraped out the side on that. I know as a midshipman, we went to a place called Havre de Grace, which is in Maryland. It's the home of a Revolutionary War naval hero named John Rogers. Only most of the time, he's a very famous naval officer from the Revolutionary War, but no Navy ship can get up there. Only our little YPs could get up there, and even our YPs were only about 2 feet narrower than the channel, and about 6 inches, and the channel was about 6 inches deeper than our draft. So you had to be like right in the middle to get up there. But good time because we were the only Navy ships that could get up there, so the town usually treated us pretty good to sell it because they like to celebrate the fact that they were the home of John Rogers on that. We still name Navy ships. There are Navy ships named after him still on that. Anybody have more time on that? Okay, last slide. Now, the slope of a line can also give you information. The slope, that M value. In fact, when you make lines, it will tell you the slope and things like that. Now, for rates, things like rates, those rate graphs, they'll tell you something. It's like slope of a distance time graph is velocity. The slope of a velocity time graph is acceleration. So if it's a straight line, it's going to be a constant. In fact, that's what you're going to be looking at next time when we graph. If it's straight, it's a constant. If it's curved, it's not a constant. This is also where calculus would come in. All right? Straight lines we deal with because we're going to deal with constant accelerations. But what if we don't have a constant acceleration? Constant acceleration, when things fall, you drop a ball, and there goes constant acceleration because gravity is constant. But if you're driving your car does it always accelerate the same amount? Like if you're going on the freeway and you push the gas down, does it accelerate, does it gain speed the same amount in the beginning as it does at the end? No. So it has variable acceleration. That's where Newton invented calculus. That's where calculus comes into physics. We don't do calculus here. That would be the AP class. But calculus deals with curved lines on a graph. We're going to be dealing with straight lines on graphs, okay, on that. But just to show you, we have a distance formula. Remember we talked about that final velocity that we got here? Our final velocity equals our starting velocity plus acceleration times time. This is, for a constant acceleration, this is our formula how to find velocity. This is kind of what you did here. But I want to show you. You might recall a line. Right? Remember that formula? It's the formula for a line. Y equals slope times the x value plus b. Well, we have to think on a distance time graph. Where's time? Is time on the y or the x? Or actually a velocity time graph. It's the x-axis. Velocity is the y. Let's rearrange this a little bit. Notice our velocity equation is the equation for a line because we are dealing with a constant acceleration on that because this formula only works for a constant acceleration. So you can see where this formula that you learned in algebra gets applied directly into finding velocities in physics on that. So just wanted to show you that. That's it for notes today. Make sure you make your summaries of what we've done today, your paragraph summary there. Those groups who have not finished crunching your numbers, you can finish crunching your numbers. What? Your paragraph summary. Every time we finish our notes, we make a paragraph summary. Every day we finish our notes. You should have that paragraph summary for that day's notes. So you think about what things did we learn today. So we learned about We learned about speed, we learned about acceleration, you did this thing, you did your exercise, and we talked about graphs. So a little summary of those things. So those groups have finished crunch your numbers on that. And then you have an option, you can start your homework. On that, you can get started your homework, probably get a good chunk of it done. We got about 15, 20 minutes or so left of class. I also put on something of entertainment value here in a second. All right?
What's the video?
You'll see. What? Anybody still need more of this? Everybody got this down? Anybody need more time?